great pleasure to welcome again Ronnie Goossens, who has kind enough to come along last semester. At the heart of modern semiconductors is lithography. Although most of the other steps are also vitally important, lithography is the art of patterning a chip. We are very privileged at Purdue to have a literal resident expert who also teaches a class on this subject. Ronnie Goossens from ASML. I think you were there since 2005?
Correct. Yeah.
So throughout the entire time of the development of EUV and the deployment of EUV. So it's a fantastic opportunity to listen to his experiences and learn more about the subject that everyone who owns an Apple device, any one of us who own one of the very modern cell phones, are using the benefits of their technology.
Hello and welcome everybody. Thanks for having me here a second time. So yeah, quick introduction. I studied physics in the Netherlands, came here in the 1980s, had always been interested in computer modeling, worked at Stanford University for a short while, apologies for that, and then worked for the Semiconductor Research Corporation. That's where I first met Mark Lundström, so we go back quite a long time. Computer modeling and simulation has been the common theme throughout my whole career. I ended up the last 20 years with a semiconductor equipment maker, ASML. They make the lithography equipment that does all of the patterning for our chips, and that's what I'm going to talk a little bit about today. Now, a big part of your career is going to be your network. So grow it, get your phones out. This is my, you can link with me in LinkedIn. And if you don't get it in time, I'll show it again at the end of the presentation so that you have another chance. I'll count to 5 and then I'll move on because I have I have a lot of material that I want to go through. I may go very fast. Don't worry if you don't get everything, and there is a lot more material on the slides available for Q&A if you want to. I have some time left tomorrow, and key is try to understand and catch on to the high-level concepts. So let's start with, we at ASML, we see that the world is actually shifting. It's instead of chips everywhere, we're moving to a world where now AI is everywhere. And that is a consequence of some major underlying forces in society, societal and economic shifts. We move all to a connected world. Climate change, resources, and that has impact on all these parts of society and industry, whether it's healthcare or transportation or agriculture. And just to give you some examples, now, you know, John Deere has launched its first autonomous tractor. Tractors now move through the fields automatically. You can now actually buy this robot from France that is fully open source, comes with sensors, actuators, and everything, is relatively affordable, not as an individual, but as a university easy, and you can experiment with very advanced robotics. NVIDIA is saying, why should your next computer be a laptop? Why not have a supercomputer that is completely AI enabled? And they're in the process of making a supercomputer about this size, not larger than a traditional hard disk, that you could actually hook up and you have your own AI platform to experiment with. You can grow your own herbs and your own vegetables in the newest product launches from Korea. So AI is, you can buy a mirror that while you stand in front of that mirror will actually scan your whole body and give you a report on your health, on your blood pressure, on your weight, on everything. So AI is really everywhere, and it impacts all these segments of industry, and with that it also impacts all of these segments of semiconductor manufacturing. Here you see an overview of, on the left-hand side, what we call advanced segments, advanced logic and memory, and on the right-hand side, more the mainstream, optical sensors, other sensors, power, analog. The move towards AI means that there are sensors, there are memory, there is computing everywhere in all of our devices. when Rose Castaneras was here from TSMC, and she did a presentation on, for this seminar series, she asked, with how many chips do you interact every day? And I found that a really interesting question. Which of you were here for that seminar that she gave? Okay, the vast majority of you. Then I'm not going to ask the question again because you already know the answer, but it's really thousands of chips every day, right, that we interact with. And so they come from all of these segments. Now, all of that growth is also going to mean that there is going to be a lot of growth in the industry. And we are convinced that by 2030, the industry will have grown the semiconductor IC manufacturing from where we are right now, around 400, 500 billion, we will have grown to about 1 trillion. And there are optimistic people that say it will be even larger. With all of that growth, there is a lot of money available, a lot of money for innovation, and that innovation means that a lot of engineers are working on exciting new developments to make all of this happen. So let's look at some of what has driven that in the past. In the past, it's always been scaling of the devices, make the devices smaller, make them work at a lower voltage so that they consume less power, and then you can have more of those devices on one chip, and that makes them more powerful. And we call that Moore's Law, and I wanted to quickly play for you this video here.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip. A pretty wild extrapolation. And it turned out to be ridiculously accurate. One of my colleagues called this Moore's Law. Rather than just being something that chronicles the progress of the industry, it kind of became something that drove the progress of the industry.
So two things. First of all, Moore's Law is not really a law of physics, right? It's something that we agreed together as a pole somewhere that you plant. That's where I want to be in the future. And when you collectively all say that's where we're going to be, everybody believes that it's possible and the innovation happens. Second thing that I wanted to mention is, did you hear that? He went from 60 transistors to 60,000 transistors on a single chip. And that was a remarkable extrapolation. So how many transistors on the latest Blackwell chip that NVIDIA just announced? I'm going to throw out some numbers, and then I want you to raise your hand if you think that I'm roughly in the right ballpark. 1 billion transistors on one chip. 5 billion. 10 billion. 50 billion. Okay? 100 billion. 200 billion. Actually, 280 billion transistors on a single chip, the latest NVIDIA chip that was announced. That's an incredible amount, right? So he extrapolated from 60 to 60,000, and here we are so many years later, and largely we are still on that same trajectory. That's the power of setting yourself very specific goals and saying, I will get there. But things have also changed, and they continue to accelerate. Here you see adoption curves for technology. And what we plotted here is how long did it take to get to 100 million users. For WhatsApp, that took about 49 months. Facebook was a little faster. Snapchat, Instagram, TikTok. ChatGPT went from 0 to more than 100 million users in under 2 months. So the pace of adoption of new technology is incredible, and that's the power of AI, right? Now, all of that requires computing. Here you see a curve of how we were able to put more and more transistors onto one chip. Let me translate that for you into what does that mean from a compute power. If we assume that 1 million transistors running at 1 gigahertz can do roughly 1 gigaflop, that is the number of floating point operations per second. I can translate that transistor count into gigaflops. And we see now the increase in the number of gigaflops. But this is what is happening with these large language models. For a long time, that's the gray curve, you could see that they were also growing at that roughly 2x per year. So the hardware was keeping up with the demand. But now, ChatGPT-3 to ChatGPT-4, what do I see? ChatGPT-3, 175 billion parameters in that model. ChatGPT-4, it is really markedly better. It gives you significantly better answers. 1.8 trillion parameters in that model that all need to be trained. That's why all the training is consuming such an incredible amount of power, right? So we see now that the demand is really driven by the training of these large models. And it also has consequences for power. So in the past, I said, we make transistors smaller, we drop the supply voltage, so the amount of power that is associated with a certain unit of compute is going down. That's the red curve here. Even although the amount of computing available went up, the power has been going down by about 0.6x per 2 years. But if I take that in combination with the demand for much more, what I find out is that unless we do something very dramatic about the power that is needed for our compute, and we extrapolate that projection that we have currently, before 2035, within 10 years from now, all of the energy produced in the whole world will only be used for training AI models. Now, obviously, that's not going to happen. Obviously, that's not sustainable, so we need to do something about it, right? We need to make sure that we get much more compute at much, much lower power. So how are we going to do that? Well, I'm going to talk with you about 4 major developments. One is the models themselves will become more efficient, and 3 of them are really from improved chips. So the models themselves, more parameters, but somehow I need to create those models with more parameters so that they still use less compute in training. Then the computer architecture itself will improve, and when you have lectures here from people of NVIDIA and Qualcomm and Intel, they will talk a lot about computer architecture. Of course, transistor scaling, that is something where Mark and I have spent a large part of our career on making that happen, and that will continue. And we at ASML also try in the production process to make sure that the production of all these chips is far more sustainable and takes less power, because you should also take that into account. Let's first look at that first component, the model efficiency. What I've done here is I've said the expected amount of compute for a model, if I'm stupid and I use brute force models, more parameters is more compute. A larger data set that I train it on is more compute, so I multiply the two, and I use that, I call that the expected compute. Then I look at what is the real compute that was needed to train the model. That's the actual compute. I divide the two and I put them on a log scale, and that's what we've done here. So if we were at 0 here, that means that the expected compute and the actual compute is the same, and that's what you saw happening there around 2005. People were not yet very smart at training these simplistic models. By now, you can see that on this natural log scale, we are up to a little bit more than 20. So the training of our large language models has become 1 billion times more efficient compared to the brute force methods of just 20 years ago. That's stunning. That's purely algorithmic improvement. If I now put that on that scale that I just used, you can see here that, say, ChatGPT and so on, and you see this big gap, right, between what we need and what we can get from the chips. This wedge that you see opening up here. And then there was all the talk about DeepSeek and stuff like that. Well, this is what DeepSeek does. It helps us make that wedge a little bit smaller. Great. Fantastic. Keep going. Develop even more efficient models. Give me more of this. But we also need to make those other components happen, and that's where we are present. So on the architecture side, one of the interesting developments is processing in memory. The top bar here, what you see is traditionally you had a CPU and a GPU. That's what would do all the compute. But they needed data. They got that data from DRAM. So through some additional core logic, that data would be put on the CPU chip. That's where the compute would happen, and then the data needed to be moved back. In the earlier versions of the NVIDIA AI systems, 80% of all of the energy was spent on moving the data. Only 20% was actually spent on training the model. So let's get rid of that. How could we potentially do that? Well, is there some part of the logic that I could actually move from that CPU, GPU directly into the memory? A lot of these algorithms are, multiply, accumulate is one of the operations that happens all the time. So what if I could do the multiply, accumulate directly in memory and I never needed to move the data, and all I need to communicate to the CPU is the result? That can give us very significant improvements. We think that we can go at least 10 times faster with, in terms of power efficiency, probably a 7x improvement. Pure chip architecture improvement. We also make the transistor smaller. Here you see a roadmap from Luc van den Hove from IMAC, and you see the FinFETs. So way before that here, remember when we had scalar MOSFETs, planar MOSFETs? That's where Mark and I started, right? And we had planar MOSFETs with a gate on top, and you had a source and a drain here. And then we tried to make them shorter and shorter, but then you got narrow channel and you couldn't control the current here in the channel anymore with the gate from above. So what did we say? Well, if I take that whole channel and I fold it up like this, now between source and drain, I have a gate that wraps over it. So from 3 sides, I now have electrostatic control over the conductivity of the channel. Right? That became the FinFET. That was great, but if I wanted to have more current out of FinFETs, I needed to have multiple fins because I couldn't make them higher. The width of the transistor basically had become the height of the fin. So now I needed multiple fins next to each other. Well, that's going to take up extra space. So why don't I take that fin, move it like this. Now I can have the gate on all 4 sides. And now I can also stack them in multiple of these sheets, and that's when we moved to the nanosheet transistors. Next move will be to see, can we make CFETs, where we now take an N-channel and a P-channel transistor and put them on top of each other. And then past that, how do I now go even further? Well, if I want to have even more control over the channel conduction, I need to make the channel even shorter for more density. So now we need to go to 2D materials. If I take a 3D material as a channel, the electrons moving will scatter up and down. They will hit the interfaces with the rest of the material. That affects the mobility, so the current will start to collapse. In intrinsic 2D materials, the electrons only move in 2 dimensions. They no longer scatter from the interfaces. There is no collapse of the mobility. So that's where a lot of material engineering is coming in. That all about transistor technology. Let me talk about the 4th component, which was how do we now make the production of all of this a lot more power efficient and sustainable. And you can see here a short loop of how every layer in a semiconductor is made. You've probably seen that in one of your earlier classes, right? We deposit a layer, we put photoresist on top, we expose it, we create all of the patterns in resist, we use some etching or ion implantation, and then we're done with this layer and we repeat that over and over again 40, 80 times, on some of the most modern chips already more than 100 times. We at ASML try to make this process a lot more power efficient. So how do we do that? Well, make sure that for every time that you do it, that you simply have more good transistors. Secondly, try to simplify the overall flow. Thirdly, make sure that the power that you need for each iteration, for each cycle, that you use less power. Let's first look at, and that's how we are going to make a contribution of another significantly decreasing this gap on where we need to be for AI. I'm not saying that we know exactly how we will ultimately get, let's see, I think I can, pointer options, laser pointer, yeah. You see, you can see, I don't know how to get here, right, to this point, but at least we have a roadmap where algorithmic efficiency will continue, we will continue, and we will continue to narrow that gap. Very much like Moore's law, we will have a law on AI compute efficiency. As I said, ASML contributes mostly through scaling. We started a long time ago with deep UV scanners, where we would use laser light of 248 nanometer, later for 193 nanometers to do our imaging. Then we switched to EUV, light that's suddenly 13.5 nanometer, very, very short. We see 400 to 800 nanometer wavelength, right? So 13.5 nanometer is much, much shorter than what we can see. We did that on systems with a numerical aperture of 0.33. If you want to know what that exactly means, when you get further in your education, take one of my classes about imaging at the resolution limit. But basically think of 0.33 as an indicator for how complex the machine is. We're now in the process of introducing 0.55 NA. Just this morning we announced that we now have 5 of these machines that are at customers and operating at customers. And that sounds like not very much, but these are not the cheapest machines. You know, they sell for multiple hundreds of millions of dollars each. We have on our roadmap for past 2030, 2035, also options that we're now looking at for Hyper-NA, where we will go to 0.75 as a numerical aperture. And that means simply that you can make the transistors smaller and smaller and smaller. The more you can simplify your life, the better off you are. And for ASML, that means how do we make sure that we deliver a lot of value? Well, the value that ASML delivers is we want lots of good printed transistors for low cost for our customers. And good printed transistors is we need to work on the yield at the best possible resolution so that you can make small things with very good accuracy so that they land on top of each other, that the overlay between all of these patterns is good, that a via actually lands on the metal that it's supposed to land on, and that the next metal that it should connect to, that via really sits in the middle. And of course, productivity. Those are all positive factors. And yeah, our system cost is, as I mentioned, several $100 million for one machine. So customers are worried about those costs. We try to fight that by making sure that, yeah, the system cost may be high, but look at the productivity and the accuracy. We, of course, also work on lifetime. All the systems that ASML has made in the last 40 years, more than 80% of all those systems are still operating today. And the older technology is now used for less critical layers, but really every system has decades of life cycle. We try to make sure that the operational cost and the environmental cost and all the power that we're talked about is part of the environmental cost, that we also control that. And with that, we are able to make things smaller and smaller. And here is a little bit of a layout of the system to give you a feel. This is roughly laying it out from that wall to here, about this deep, and yeah, roughly that high. That's about the size of one of these systems. On the top left, you see where the reticles come in. Those are the blueprints that hold all the patterns. Through that robot, they are moved there to the top, where you see the reticle move back and forth. On the bottom left, you see the wafers come in through a wafer handler, and that moves it to, I'll point out two things here. Here is a first wafer stage. And you can see that we take measurements there, overlay measurement and height measurements. Those real-time are fed forward so that when that wafer moves to the exposure stage, we adjust everything there so that the imaging is optimal for the overlay of an alignment of that wafer. Here is then where the actual exposure happens. And the exposure means the light is coming from here, the source. I will tell you more about the source. All this optics is to illuminate the mask here. That mask is scanning back and forth. I'll tell you more about that. And this is then the projection optics. So that's in a very simplistic form, the high-level design. Thank you. Clearly, I need to go fast. So first of all, cost, uptime. We're now at a point that the vast majority of our systems is approaching 95% uptime, which for systems of this complexity is actually quite good. The productivity goes up. When we first introduced EUV in 2019 into volume, we were processing just over 150 wafers per hour. Now we are 220, 240 wafers per hour. So productivity has nearly doubled for these machines. At the same time, here you can see the overlay. How well can I put one pattern right on top of each other? And here you see the older systems, the 3400s, then the 3600, and now our newest system. We consistently can place patterns on top of each other with an accuracy below 1 nanometer. And that, while you saw that reticle stage move back and forth, right? Well, that gets accelerated with 15G. We need to, at any point in time, control the position of that reticle within tens of picometers accurately to be able to ensure the overlay that you're getting. Process simplification. Here you see how simply by having a system with more contrast, instead of having layers that I need to create by doing multiple exposures, I can now say, hey, I can make that pattern in one go. So even although the machine is more expensive, it simplifies the process, and that still net is a lower cost of technology for our customers. To clarify that point a little bit further, here's a small animation of what happens. On the left-hand side, I have metal. I want to connect that metal to something else. I don't have the resolution to move in, to have a pattern in two directions. So I first, through a V, I need to go to another metal layer. Then I need to connect in the other direction through that second metal layer, and then I need to go back, just because I wanted to make a jog in my layout. With a high-NA machine on the right, with much better contrast, boom, done in one process step. So even although that requires much more contrast, a more complex and more costly machine, net the cost of technology is still lower. Here you can see some of the examples of the quality that we get here. So those 280 billion transistors that we talked about translate into more than 1 trillion contact holes, because every transistor needs to have multiple contacts, right? More than 1 trillion contact holes on a single chip that all needs to yield, because there is no redundancy in contact holes. There is simply no room for that. Here you can see on the bottom that when we try to get contact holes with a pitch below 32 nanometer, we simply start to get failures. Even when we use a very large dose of 73 millijoule per centimeter squared, that is to reduce the stochastics, simply by going to a machine with a higher numerical aperture, more contrast, I can simplify. I can now work at 45 millijoules. I get more productivity, and I have much, much better imaging, and I've bought myself a roadmap towards smaller pitches. This doesn't come for free. These machines are quite complex. Here you see, and you can see the person standing there, just the metrology equipment that is needed to measure the quality of the mirrors that we use in the optics. And since we are here at Purdue, so if I have a very accurate mirror and I polish it to an accuracy of only 20 picometers, then I also need to control the angle of that mirror very accurate to get the imaging, to get that overlay, right? Well, if I take that angular precision, I say, what if I illuminate it with a laser and I shine it to the moon, and Neil is still up there and he drops a penny and he says, can you hit that penny? Can you aim that mirror so accurately that you hit the penny? Our answer would be, would you like us to hit the left side of the penny or the right side of the penny? That's roughly the amount of accuracy that you need. Here is how that light source works. We shoot tin droplets in vacuum, molten tin. We hit them multiple times with an infrared laser to make that droplet take the right shape, to vaporize it, and then to turn it into a plasma. And then that plasma is what emits the EUV light. The mirror that you see behind it is then the collector mirror that kind of aims the light to go into the scanner where it's used for imaging. Here you see a small video taken at about 3 million frames per second. We shoot these tin droplets 50,000 times per second. And here you see it start to get the right shape. And in just a second, you see it being hit the second time by the infrared laser there. And that's when it turns into a tin plasma that emits the light. Of course, you need to make sure that that tin plasma doesn't land on that beautiful mirror that you just had. Lots and lots of technical problems, but we're able to overcome some of that. And now we can generate 1 kilowatt of EUV light, which is very essential. So I also talked about the roadmap. We move more and more towards a modular structure for all of this, reusing more and more of the modules. That, again, helps with decreasing the cost. The high-NA systems are anamorphic. I will talk about that in my class on EUV lithography that you can take in perhaps in 2 years from now or in 3 years from now. If I can go to larger reticles, 6 by 12, then that helps with the productivity because I can scan faster, but that requires the whole industry to move with us. And I'll just quickly go towards the end here. I told you that we have a lot of layers, and not all of the layers are equally critical. Here you see how a chip is built up of all of these layers, and the higher up you get, the structures are bigger. You can use some of our older systems to do that, but we make innovations everywhere. Here is a material innovation on the wafer table. When I move these, if I have a sheet of paper that I put on this table, it's nice and flat. But when this defect is sitting here and I put that same sheet of paper here, it wobbles over it. That deforms the wafer. That leads to overlay problems. So I cannot have a single defect sitting on the wafer table when I put those wafers on, even after I've passed millions of wafers through. So how do you actually put a wafer on a wafer table and take it back off without ever having a single particle come off? Well, we now use very advanced diamond coatings to help that. So there is a lot of material science involved in all of this. In the interest of time, I will skip some of these slides about bonding, but people are now saying if I can get my logic chip, and what if I can glue the memory chip right on top of it? And I could make hundreds of thousands of connections with through silicon vias between those two chips. Then I can have much more bandwidth between my memory and my logic with very short path lengths, so that's low capacitance, low switching power, etc. And then finally, we see the innovation in packaging. So the innovation in packaging means that people are now saying on an interposer, I can put perhaps GPUs and CPUs and memory and put all of that together, but that interposer is also itself now made with semiconductor technology. So we get all these challenges that we have 6 substrates if we want to put optoelectronics in it. We have multiple reticles that all need to be done. We have in particular, much larger field sizes. So we are launching new products that can handle much larger field sizes, specifically for these advanced packaging applications. And the last part that I wanted to quickly mention is yield. None of these machines, as good as they are, would give yield if I weren't constantly measuring the results that I get and use that metrology data to feedback on how do I adjust the scanner so that it gives me even better performance. And here you see how that has contributed over time. Over time, you see the number of parameters that within one lot, 25 wafers, how many parameters can I communicate to the scanner that it should optimize so that the imaging is better. And you see this explosion. We now have more than 100,000 parameters for every 25 wafers. Now remember, 25 wafers is just 5 minutes, right? So every 5 minutes, 25 wafers go to the scanner, and they need to go with 100,000 parameters that I've computed based on metrology that I've taken and control algorithms on how do I control this. So metrology and metrology throughput is critical, but it has allowed us to do this with the overlay ultimately. And if you then combine that with advanced computational lithography, we've even been able to do a little bit better than that. I'll skip over all of that in the interest of time. For some of the most advanced metrology, because if we don't have the right metrology, these algorithms don't work, then our machines don't work. And as I said, I need lots of measurements very quickly. So E-beam systems are the only way to get that kind of data. And then you need lots and lots of that data. So what we now do is instead of having one electron beam scanning and then perhaps finding a defect somewhere, but I didn't look in the right spot, right? So I need to look everywhere. What we now do is we try to say, hey, perhaps we can scan a whole bunch of locations all in one go. And that's now with the eScan 1100 and E-beam system with 25 beams. And in our newest system, we are now having next generation where we have more than 2,000 electron beams all together in one system with with MEMS devices, where we really multiply the productivity of the metrology tools by factors of 1,000. So, in short, what I've told you is AI drives an incredible amount of demand. It pushes for improvements in all kinds of areas, from algorithms to equipment. We try to address that by creating tools that are more productive, give better resolution, give better overlay, and at the same time consume less power and all of that. So that's the technical part. I can't stop without having a very quick plug for the company also. We have 45,000 people by now. We're present in all kinds of locations around the world. Here is an example of some of the sites and what we do in the various locations. And we need engineers like you that graduate in a few years from now. And whether you're an electrical engineer, hey, if you're good and you're curious and you're innovative, we want you. If you're in mechanical engineering, we need you. If you're in material science, we need you. If you're in industrial engineering, we need you. So the message that I want to leave you with is Gordon Moore was perhaps 50 or 60 years ago, and I had a career of 40 years in the semiconductor industry. But there is at least 20 or 30 years of great innovation in this industry happening. And you guys will all be ready for that as long as you make sure have a solid foundation in sciences, learn to apply that to real engineering problems, and above all, keep your curiosity alive. And with that, I'd like to wrap up and open for Q&A. Thank you. And apologies, I said it was going to be a lot and that I had to go fast, and I think that's what I did, but I hope you still got the overview.
Well, thank you very much. Anyone here with any initial questions?
I was just curious, with the lithography machines, do you guys outsource any parts of like the motion control systems or stuff like that?
So the question was whether we outsource. Yes, we look at ASML to, for example, Zeiss in Germany is our partner for our optics. You can see that here on this graph. Easier to do that this way. In Oberkochen, in south of Germany, that's where all of the optics is done. We don't do that ourselves. In Ditzingen, that's where they make the large EUV machines. The light source is in San Diego. That used to be Cymer, a separate company. We were happy having that outsourced, but for the EUV machines, the investment that they needed to make financially did not make sense for them. So we acquired them because it made sense for us. They're now part of us, but that used to be outsourced. These glass coatings, diamond coatings for the wafer tables, that used to be a separate company, Berlin Glass. We acquired them a few years ago. So very often we work with vendors. We try to outsource, in fact, as much as possible because we see each other more as system integrators. But when it's necessary, we don't shy away from saying this is absolutely critical. We'll take ownership for it ourselves.
So do you know there's a company in Indianapolis that makes the frame for your machine?
I do, yes. Correct. And these, by the way, these frames, I go on the internet and look at the first high-NA machine that was installed at Intel. The base frame is literally this big. And the accuracy requirements are such that any hole that I drill here to connect anything here compared to any little hole that I drill over there and tap over there should be within a micron in the right relative position, right? So it's fascinating technology. And in all of these elements, there is constant innovation that needs to be integrated. Very good question. Thank you.
I'm just curious, kind of like, how does ASML organize and like kind of integrate all these different engineering fields and science fields to kind of make these technologies like EUV?
Yeah. So if I heard it correctly, how do we organize internally with so many engineering disciplines, right? Some of our most highly valued engineers are the system engineers because they really look at all these modules. What is the performance that we need from this module? What do we need from this module? What do we need from that module? So that the system as a whole actually accomplishes what it needs to do. That's why those people report directly into the head of our technology and research. Then for the rest, the majority of the company is organized for the scanner business around competencies. We have people that really are experts in positioning systems. They know more about Fabry Pro interferometers and other things than anybody else. We have experts, for example, in Wilton, in mechanical engineering, that reticle stage. I said it accelerates at 15G, right? That's because if I expose more than 180 wafers per second, or sorry, per hour, that's 15 seconds per wafer. If there are 150 fields on a wafer, that's only 100 milliseconds per field. So within 100 milliseconds, I need to accelerate from 0 to 4 meters per second, then move with picometer accuracy, and then slow down so that I can start going in the opposite direction. All of that within 100 milliseconds. At 15G, what are the vibrations that you introduce? So mechanical engineering is a really big part of what we do. And then, of course, we have a very large software department because all of this needs to work together, and the control software on the scanner is very large. So we're organized along a number of these competencies, and then orthogonal to that, we have a project organization that says, oh, for this large project, I need this from this group, and this from this group, and this from this group. So cross-functional coordination and understanding is a really, really big thing.
I just took a closer look at the map, and I don't quite understand why there'd be a clamps factory in Berlin. Can you explain?
Sorry. Why?
There's a clamps factory in Berlin. I don't exactly
Yes.
understand why that'd be a major component in lithography machines. Could you go a bit more into depth about that?
So the reticle needs to be held to that reticle stage, and you could see from that exploded view that the reticle was hanging upside down, right? Because the light was coming this way. So that needs to be clamped against the reticle stage, so that at 15G you don't want the reticle, each of these reticles, the blueprints, just getting that manufactured is so complex itself that a single reticle nowadays is more than $1 million. So you don't want that to go flying all through your scanner, right? You want that to really be clamped. But what happens when I clamp something down really, really strong? It deforms. And when things deform, that mucks with the overlay, because now the patterns are not in the right position. So how do I clamp something in such a way that it deforms as little as possible, and if it does deform, it better be 100% reproducible so that I can correct for it, so that it becomes one of the inputs in these hundreds of thousands of control parameters in my feedback loops. All right? And by the way, keep going, because I love this part. So,
I have one question more about you.
Yeah.
So from what I saw, you're with ASML and Purdue. How's that working? What are you doing here, and what are you doing with ASML?
okay, yeah. So I, as I said, I worked for ASML full-time for 20 years. A few years ago, I came to the conclusion that there were a lot of other things that I also wanted to do in life. So I told my boss that I wanted to work part-time. I now work roughly 1/3 of my time for ASML. Probably 1/3 or half of my time is spent on working with Purdue, on teaching here, and working with Mark on some new initiatives. I am on the board of the Boys and Girls Club, giving back to the community and providing opportunities to underprivileged kids. So that's 1/3 of my time. 1/3 of my time is staying fit and going to the gym and outdoor activities, and 1/3 of my time. Am I over a total of one? Yes, I'm very busy. I love photography. I just came back from 2 weeks in Chile, so I'm at a point in my life that I am partially retired, but retirement for me doesn't mean that I sit at home behind a cup of coffee, but it just means that now I only get to do the things that I feel valuable and that give me joy. Yes. Yeah.
Well, thank you very much.
And
Are you available for a few minutes after the class?
Yeah, of course.
Okay, then.
That one, right?
So
Yeah.
thank you very much, Ronnie, and everyone feel free to